Hello class, today we're going to learn about quadratic word problems. So you've learned all the tools you need to solve every word problem so far. One of the things we're going to go back to first before we get into that is just reviewing again all the different forms, the equations you might see come in. The standard form, the factored form, and the vertex form. We've discussed this rotation back and forth between how you go from one form to the other. So from standard to vertex form, it's that completing the square. And then from standard to factoring form, we would factor. And then to go back from factored form and vertex form back into standard form, you have to expand and multiply. And then we've discussed on several occasions what each of these forms give you. So for example, the standard form will only give you the y-intercept on a graph of the quadratic. And keywords to think about when you see a word problem is things like the starting point of something, when t is equal to 0, what's the initial height or the initial value? That's what the y-intercept does, and it's always this value in standard form. Then when you go to vertex form, you get the vertex, which is h and k. K is the max or the min value. So when you're talking about height, you're talking about area, if you're talking about profit. H then, that value of h is yes, it's the axis of symmetry, but it tells you when and where did that max or min occur. So when did you reach that maximum height? When did you reach the maximum area? What dimensions were they? So that's the h. If you go to factor form, what that tells you is your x-intercepts. So things like the zeros, a break-even point when you're talking about profits and revenue. When did something finish or hit the ground? So these are the when aspects, okay? So we've talked about these methods, but the one thing that we've learned also this unit is how we go from standard form and skipping, bypassing the factor form, and just to find the x-intercepts, you would use the quadratic formula. So you can go from standard form to factor form using factoring, but if you just want to quickly get your x-intercepts, though it's not a very quick method, it's using the quadratic formula. So don't forget that. So as I mentioned, you might see in word problems some words like max, min, largest, least, or smallest. And so you're looking for that vertex, okay, the optimal value. When you hear the words solving for a value, so I want to solve for when something happens, or if I want to solve for when it hits 0. When it hits 0, the x-intercepts, right? That's when you know the y equals 0. So make sure you write that in when you're solving those equations. So you're going to set up for the equation for that value. You want to make sure that the equation is equal to 0. So transform it so that's 0 on one side of the equation. And then you can use factoring or quadratic formula, or you can graph it to find the actual value that they were wanting. And then if you hear the word starting or initial amount, that's when you look for the y-intercept, and make sure that when you're doing that the x value is equal to 0 in the equation. Okay, so let's try out some word problems that you might see in this case. So for our first example, we have a rectangular park measures 100 meters by 60 meters. So right away, when I have these word problems, I want to draw a diagram. And in this case, a rectangle. And we know it's going to be 100 meters by 60 meters. A path of constant width is to be paved around the perimeter. So we know we're talking about around this. The mayor wants to be sure that the path does not reduce the area of grass by more than 10%. What is the maximum allowable width of the path, rounded to the nearest tenth of a meter? So this is our park, and we would assume that around the park is a road. So that means we're cutting into this park. So we're going to cut into this park, and we're going to create a pavement, a sidewalk maybe, around the park. And so this would be the paved area over here, and the grassy area would be in the side. Okay, and so now the question says that it wants to not reduce the area of the grass by more than 10%. So whatever the area initially is of the park, we can't reduce it by more than 10%. So a good thing to do here is to figure out what the original area would have been. So the original area is a rectangle, would be length times width. So in this case, it'd be 100 meters times 60 meters. So you end up with 6,000 meters squared. That's how much area is in the blue rectangle. So if we want to make sure that let's find our limit to how much we can reduce this by. So if we want to reduce it, we can't reduce it by more than 10%. So the area left over has to now be the 6,000, which was the original area, and has to be reduced by 10%. So 10% means we have 90% left over. And 90% means that I'm going to multiply the 6,000 by 0.9. And that means we end up with 5,400 meters squared. So that means that the area left over, the green grass that's in the middle, has to have an area of 5,400 max, right? You can't have anything less than that. So obviously we can see that we don't have an equation, but as we've been talking a lot about this, we want to know about area, and we want to make sure we maximize the area to 5,400. So we know that the area equals length times the width is the formula I'm going to work with, but we don't know the dimensions of the new area. That's really what we're trying to find, the maximum allowable width, right? So to get this dimension, you might have to create a variable. In this case, we'll call this length of the, the width of the pavement to possibly x. So write your let statement. Let x represent the width of the pavement. Okay. And so now we can create dimensions for that smaller area, which has to have at least 5,400 meters squared area. And that's going to be, if you look across this way, this was 100 meters. So now we have to reduce it by the x on this side and the x on this side. So therefore, this dimension is 100 minus 2 x's, 1 x from this side and 1 x from this side. That would give us this space here. Okay, and you could do the same going upwards. Upwards, it's going to be reduced by x up here and x down here. So this is going to be 60 minus 2x. So that's going to be my new dimension of the grass that's left over. So we can write that into our area formula. We need to have this equation to be 100 minus 2x. And the other one is going to be 60 minus 2x. And the area must be 5,400 is the max. We can't have it any less than that. So I'm going to write out the equation. And then I'm just going to expand and simplify that. So I get this expression. And then remember, when we're solving an equation, we must make this equation equal to 0. So I'm going to bring 5,400 to the other side, and I'm going to simplify this expression. And then I'm going to collect my like terms, and I'm going to rearrange this so that it's the x squared first. So now I have 4x squared minus 320x plus 600. And so when we're solving for an equation, that means we're finding our x-intercepts or our values. So then you want to use either factoring or quadratic formula. And because I don't want to factor this, I will use the quadratic formula. So there's my quadratic formula and my values filled in. Now I'm going to first figure out what's under the square root. And now I'm going to separate these into the positive version and the negative version of the square root symbol. And when you break it down into the plus and the minus, for this side you would get an x value of 78.07 or 08, meters. And the other one will be 1.92 meters. So now when you look at your answer, always go back to the question and ask yourself, what did x mean again? Well, x is going to be, we said, the representative of the width of the pavement. So does it make sense for this width of the pavement to be 1.92 meters or 78.08 meters? Well, 78 meters would take over the entire width of this, so that does not make sense. So it makes more sense that the answer is, therefore, the width of the pavement is going to be 1.92 meters. Although it says to the nearest tenth, so I should really reduce this down to 1.9 meters. Okay, so always make sure that when you're going through and solving, always look back to your answer and decide which one makes the most sense in the context. Even if you have to go back to your let statement, which is why it's important to write let statement, or your diagram. Okay, all right, let's do another question. This one is about a triangle. So as soon as I see that, I'm going to do a triangle, and I know that it's going to be a right angle triangle because it talks about hypotenuse. So one leg of a right triangle is 1 centimeter longer than the other leg. The length of the hypotenuse is 9 centimeters greater than that of the shorter leg. Find the lengths of the 3 sides. So again, I'm going to write let x represent the shorter side because it seems that all the other legs are in proportion to the shorter side. So the length of the shorter side. So maybe I'll call this x. And then according to this, it says that the leg of the other triangle is 1 centimeter longer, so it'll be x plus 1. And then the last one is the hypotenuse is 9 centimeter greater, so that's x plus 9. All right, remember the hypotenuse is always across from the 90-degree angle. And so now it says find the lengths of the 3 sides. Well, we're talking about sides of a right angle triangle, and we don't have a formula yet. So therefore, we must think of some previous knowledge we have about that brings into the relationship of the 3 sides of a right angle triangle. And the only formula, if you recall, that we know is the Pythagorean theorem, which is a squared plus b squared is equal to c squared. So now fill it in. We have x squared plus x plus 1 squared equals x plus 9 squared. And it must be this way because the x plus 9 has to be your hypotenuse, which is c. And now you expand. But be careful. Don't forget that this means x plus 1 times x plus 1. Do not just go and square each of the terms because you're not going to get the right value. You must distribute accordingly. And if you did it properly, you would get x squared plus 2x plus 1. So you end up with 3 terms. Okay? So make sure you do it properly and do the expanded form. So x squared plus 18x plus 81. And now we're trying to solve this equation. So recall, that means I have to make the equation equal to 0. So I move everything to the other side, and then I simplify. So this is a long expression that simplifies to x squared minus 16x minus 80 equals 0. So now you either factor or you do the quadratic formula again. And this is a difficult one to factor, so I would do the quadratic formula. So you get x is equal to 16 plus or minus the square root of 576 all over 2. And you have to make sure you split that into the positive and negative version. So you either get 20 or you get negative 4. And when you look at what x represents, it represents the length of the shorter leg. Well, a negative answer does not make sense. So therefore, this is going to be the one length. So you write, therefore, the triangle sides are, now 20 is one of them. The other one's going to be 20 plus 1, so it's going to be 21. And then 20 plus 9, so 29 centimeters. Okay? Always make sure you write your therefore statements. Show both values, but then define which one is the correct value. And so just kind of make sure that you're looking for what is the question asking you for, and then recognizing what you need to do. And then it's just a matter of practice. Good luck.